Okay, good morning, everyone. Today we'll take a look at application of polynomial functions. You will have a take-home test and a problem like this, so please pay close attention. This problem is quite important in mathematics. You will see this problem a lot in calculus, but we'll take a look at it the Algebra 2 way. So let's assume here that we have a piece of cardboard. It's lying flat. And what we want to do, we want to take that piece of cardboard and we want to make a box from it. So in order to do that, what we have to do is cut out 4 congruent corners, or squares if you will. Okay, so we'll cut out that square, and this square, this square, and this square. And then what we'll do is that once we cut these squares out, then we fold up the remaining sides. So we'll take this side and we'll fold it up. We'll take that side and we'll fold it up. We'll take this side and fold it up, and that side and fold it up. And then we'll get a picture that looks like a rectangular prism, if you will, a box. Okay. So all we need to do is add some dimensions to this, and then we have a problem. So here we go. We have a bottom for a box can be made by cutting congruent squares from each of the 4 corners of a piece of cardboard. So what we're going to do, we're going to cut out 4 corners, and we don't know the sides, what the side length is. We'll just call it X. So there's one corner, another corner, another corner, and another corner. And we just don't know the dimensions, but we'll call it X. So we'll cut out those 4 corners. Now the volume of a box made from 4-inch by 12-inch piece of cardboard would be represented as the volume, which is a function of x, is equal to x times 14 minus 2x times 12 minus 2x, where x is the side length of one of the squares. And so let's ask the question, why does that formula hold? Well, let's remember the formula for the volume of a rectangular prism. The volume is equal to the height times the length times the width. Okay, in this case here, we'll say that the length is 14 inches. 14 inches. And what we need to do, we're going to cut out 2 squares that has a side length of x. We don't know what the actual side length is. We'll just call it x. But we're going to start with 14, and we're going to cut out 2 of those squares, and each square has a side length of x. So 14 minus x, well, that's just 14 minus 2x, so I'll write that there. 14 minus 2x, but that's equal to my length. Okay? So there. So there's my 14 minus 2x there. 14 minus 2x. And then a ditto for the width. So we start with a width of 12 inches, and then we're going to cut out 2 squares, and each square has a side length of x. So 12x minus x minus x. Well, that will give me 12 minus 2x. And that's equal to my width. So there's my width. Let me put the width down there. So that's my width. Let me put L down here. That's my length. Okay, so here. There's my width, and there's my length. Okay, so there's my 12 minus 2x. Now the height of that box then would just be x. It will be the height of the corners that we cut out. So that would be x. Okay, so that's my height. So height equals x. Okay. So that's my height there. So that's why that formula makes sense here. Okay. So volume then is going to equal to x times 14 minus 2x times 12 minus 2x. All right. Now, let's say this here. Okay, so in your test you'll have some problems to answer. So we want to express the volume of the box as a sum of monomials in standard form. In other words, we want to multiply height times length times width. So the first thing I'll do is I'll multiply 14 minus 2x times 12 minus 2x, and we'll FOIL. 14 times 12 is 168. 14 times negative 2x is negative 28x. Negative 2x times 12 is negative 24x. And then negative 2x times negative 2x is plus 4x squared. We combine our like terms and write in standard form. So I'll move the 4x squared to the front. And then negative 28x minus 24x gives me negative 52x. And then I have 168. So that represents that 4x cubed. It looks more like, or squared I should say, 4x squared minus 52x plus 168. That's what we got when we multiplied the length times the width. Now we have to multiply by x, or the height, and that will give me my volume. So the volume then, which is a function of x, the side of the square, is going to equal 4x cubed minus 52x squared plus 168x. Okay, polynomial. Now, question number 2 asks this. Using decimals, let's find the zeros of the polynomial function for the volume of the box. So what I've done is I've taken the liberty of graphing that. Okay, there's 4x cubed minus 52x squared plus 168x. Let me just verify. 4x cubed minus 52x squared plus 168x. And then the question asks us to find the zeros. So we have to go to where y is equal to 0. And this is such a huge graph here. Let me make it smaller. To zoom in, I'll get there faster. Okay, so there we go. Now y is 0. So I'll find my zeros here. All right, so my zeros then will be, when x is 0, there's 1, 0. So when x is 0, y is 0. It's my x-intercept. The other 0 is 6. So my x-intercept is 6, 0. And then my other 0 is 7. So 7, 0. So those are the zeros there of that polynomial function. Remember, the zeros are when the graph crosses the x-axis. That's when y is equal to 0. In each case, y is equal to 0. So my x is 0, 6, and 7. So those are my zeros. All right, so there they are. So 0, 6, and 7. My x-intercepts are 0, 0, 6, 0, and 7, 0. Let's look at the next question. Using the zeros you found in 2, what would represent a reasonable domain for the polynomial function? Remember, domain is x. And so the question is really asking us here, what values of x will give us positive values for the volume? Certainly volume can't be negative. Okay, so looking at this graph here, I see that when x is 0, y is 0. Okay, anything less than 0, I'll have a negative. It will be below the x-axis there. Okay, so x has to be greater than or equal to 0. X can't be negative. Because if x is negative, then y will be negative, and we can't have negative volume. Okay, so if I substitute in 0, 4 times 0 cubed is 0, minus 52 times 0 squared is 0, plus 168 times 0 is 0. And so again, we're looking to see where in that red graph, that polynomial will have y values that are greater than 0. We can't have negative volume. And so now if I zoom out, and it's kind of, so if I zoom out, you'll see that that polynomial is going up and up and up. The y values are positive, and then they start to decrease. They're not negative yet, but now they become negative again at 6. X is equal to 6. Okay, so anywhere between 0 and 6, that polynomial function is positive. Volume is positive. Okay, and my other 0, so but any values between 6 and 7, the function is negative. So a reasonable domain for this polynomial would be from 0 to 6. Any value of x between 0 and 6, including 0 and 6. Okay, so that's looking at things graphically. Let's look at it algebraically, make even more sense. So if I go up here, I want you to notice that my length is 14 inches. and I'm going to cut off 2 squares. Okay? Now the largest, if I'm working with 14 inches, if I'm working with my length here, the largest x can be is 7. I'm going to cut off two sevens. Okay? All right, so 14 minus 7, well, that would give me 0. So what I'm really saying here is if I look at it in terms of x, then 14 minus 2x, that length has to be greater than or equal to 0. We can't have negative length, which means 14 minus 2x has to be greater, or 14 has to be greater than or equal to 2x. If I add 2x to both sides, 7 has to be greater than or equal to x. I always move the x on the other side. X has to be less than or equal to 7. So it would seem that as long as x is less than or equal to 7, we're okay. But let's go back to the graph. Well, but that's not quite true, because anywhere between 6 and 7, the volume is negative. Okay, so that didn't work. Okay, and the reason it didn't work is because we have not considered the width when we were looking at that. We didn't consider the width. If you take a look at the width, x cannot equal 7. Okay, we'd be cutting off more than we have. If x was 7, 7 plus 7 is 14, but we only have 12 inches to work with. So really the limiting factor here, the limiting value, or the equation we should look at really is that 12 minus 2x has to be greater than or equal to 0. 12 has to be greater than or equal to 2x. 6 has to be greater than or equal to x, or x has to be less than or equal to 6. This is a limiting value. X has to be less than or equal to 6. Right? And again, you see that from the graph. As long as x is less than or equal to 6 but greater than or equal to 0, we have positive values for volume, or the volume is nothing. 0, I should say. All right. So if x was equal to 6, then 12 minus 12 would be 0. And then 0 times anything would give me 0. So I wouldn't have a box. I'd cut up all the cardboard. I would not be able to fold it up. And then if I didn't cut out anything, I wouldn't have a box. I wouldn't be able to fold it up. So the domain then will be any value of x, including 0, all the way to 6, including 6. So that would be a reasonable domain. Reasonable domain there. So explain that algebraically as well as graphically. Now, what side length then maximizes the volume of the box? Well, to answer that question, we're looking at global max or global mins. Well, actually, we're not even looking at global minimums, because I do see a local minimum here, but we're looking to see when the volume is the greatest. Well, that local minimum volume was negative. So we have to actually go up here to where that polynomial achieves its greatest value between the values of 0 and 6. Okay, the reasonable domain. And so right here, let me see here. So there, when x is about 2.15 inches, I'll get a maximum value of 160.58 cubic inches, and that will represent maximum volume. So at 2.14 inches, then we'll maximize the volume. Okay. Now, even though that was a local maximum, we can't consider points over here for that. Where's the other? Because it keeps going up. We can't consider those points there. Okay, because our reasonable domain only has to go from 0 to 6. Okay, so we consider that local maximum then really to be the global maximum from values from 0 to 6, our reasonable domain. Okay. All right, so there, so here, yeah, so from 0 to 6, wherever we get, so we're getting there, yeah. So for 0 to 6. All right, our reasonable domain. All right, so there, so you'll have a problem like that for your take-home test.